Imagine holding the universe in the palm of your hand, not as a tangible object but as a mathematical equation. This equation, the wave function of the universe, would encapsulate the entirety of existence, from the smallest subatomic particle to the largest cosmic structure. It would be the ultimate expression of reality, a cosmic blueprint revealing the past, present, and future. For decades, physicists have chased this holy grail of science, striving to unlock the secrets hidden within the quantum realm. The wave function, a cornerstone of quantum mechanics, describes the probability of finding a particle at a specific point in space and time. However, calculating the wave function for complex systems, let alone the entire universe, has remained a daunting challenge. The sheer number of particles and interactions involved creates a computational barrier that seemed insurmountable. Recent breakthroughs in quantum mechanics, however, have begun to chip away at this barrier, offering a glimmer of hope that we may one day grasp the universe's fundamental code. New techniques, coupled with advancements in quantum computing, are pushing the boundaries of what we thought possible, bringing us closer than ever to the dream of calculating the universe's wave function. This pursuit is not merely an academic exercise. Unlocking the universe's wave function would revolutionize our understanding of the cosmos and our place within it. It would unveil the deepest secrets of reality, potentially revealing the existence of parallel universes and shedding light on the very nature of consciousness itself. One of the most significant breakthroughs in recent years is the development of wave function matching techniques. This revolutionary approach allows physicists to simulate complex quantum systems, including those previously deemed too computationally expensive to model. Wave function matching works by adjusting short-distance interactions between particles to align their wave functions with more easily computable ones. This clever trick preserves the essential properties of the system while drastically reducing the computational burden. Imagine trying to simulate the motion of billions of water molecules in a wave. Traditional methods would require tracking the position and momentum of each molecule individually, a task quickly overwhelming even the most powerful supercomputers. Wave function matching, however, simplifies the problem by focusing on the overall shape and behavior of the wave rather than the individual molecules. This allows us to capture the essential physics without getting bogged down in unnecessary details. This breakthrough has already yielded impressive results. Physicists have successfully used wave function matching to simulate various nuclear systems, providing valuable insights into the behavior of matter at its most fundamental level. Moreover, these techniques are not limited to classical computers. They can be implemented on quantum computers, further accelerating our ability to probe the quantum realm. The development of wave function matching marks a turning point in our quest to understand the universe at a quantum level. It provides a powerful new tool for tackling previously intractable problems, paving the way for more accurate and sophisticated simulations of complex quantum systems. In December 2024, the world watched in awe as Google announced a groundbreaking achievement in quantum computing. Their latest quantum chip, dubbed Willow, had performed a benchmark calculation in under 5 minutes, a feat that would take the fastest supercomputers an estimated 10 septillion years. While the task itself, generating a random distribution of numbers, lacked practical application, it served as a powerful demonstration of the potential of quantum computing. Willow's accomplishment sent ripples through the scientific community, igniting excitement and speculation about the future of quantum computation. Hartmut Neven, head of Google Quantum AI, even suggested that the chip's incredible speed might hint at something even more profound: calculations occurring in parallel universes. This bold statement, while met with skepticism by some, highlights the growing recognition that quantum mechanics may hold the key to unlocking the secrets of the multiverse. Willow's success is a testament to the rapid progress being made in quantum computing. As these machines continue to evolve, their computational power will only increase, opening up new avenues for scientific exploration and discovery. We are entering a new era of computation, one where the seemingly impossible becomes possible, and the universe's most closely guarded secrets are within reach. The idea of parallel universes, once relegated to the realm of science fiction, has gained traction in recent years, as physicists grapple with the bizarre implications of quantum mechanics. The many worlds interpretation, a controversial yet increasingly popular interpretation of quantum theory, suggests that every quantum measurement or interaction causes the universe to split into multiple parallel universes, each representing a different possible outcome. While this idea might seem outlandish at first glance, it offers an elegant solution to some of the most perplexing paradoxes of quantum mechanics, such as the observer effect and the wave function collapse. If every possible outcome of a quantum event actually occurs just in different branches of the multiverse, then there is no need for wave functions to collapse or for observers to influence reality. Google's claim that Willow's speed might be due to calculations occurring in parallel universes, while speculative, has further fueled speculation about the existence of the multiverse. While it's too early to say for sure, the possibility that we are glimpsing echoes of other realities is both exhilarating and unsettling. It challenges our fundamental understanding of the universe and our place within it. Section 5. Consciousness, a Cosmic Symphony. The quest to calculate the universe's wave function is about understanding ourselves. Consciousness has long puzzled philosophers and scientists alike. How does the brain give rise to subjective experience? What ignites awareness in the universe? Quantum mechanics may hold the key to consciousness. The Orkor theory proposes consciousness arises from quantum computations in microtubules. Consciousness is woven into the fabric of reality. Consciousness may predate life itself. Quantum collapses in the early universe gave rise to proto-conscious moments. These moments guided the evolution of life and consciousness. We are part of a grander cosmic symphony. It raises profound questions about reality and existence. Section 6. The uncertain future. The quest to calculate the universe's wave function is still in its infancy. While recent breakthroughs have brought us closer than ever to this ultimate goal, significant challenges remain. Quantum computers, though rapidly advancing, are still in their early stages of development. They are prone to errors and limitations that must be overcome before they can tackle the immense complexity of the universe's wave function. Furthermore, even if we could calculate the wave function, interpreting its results would be a monumental task. The sheer amount of information contained within this cosmic equation would be overwhelming, requiring entirely new mathematical and computational tools to decipher. Despite these challenges, the pursuit of the universe's wave function continues to drive scientific progress. It inspires innovation, fosters collaboration, and pushes the boundaries of human knowledge. Each new discovery, each incremental step forward brings us closer to unraveling the universe's deepest secrets. Section 7. A universe of possibilities. The implications of calculating the universe's wave function are profound. It would not only revolutionize our understanding of the cosmos, but also open up a universe of possibilities, some exhilarating, others unsettling. Imagine a future where we can predict the behavior of matter with absolute certainty, where the design of new materials with unimaginable properties becomes commonplace, where the mysteries of the human brain are finally unlocked. This is the promise of quantum computing, a promise that hinges on our ability to harness the power of the wave function. But with this power comes responsibility, the ability to manipulate the fabric of reality at its most fundamental level raises significant ethical concerns. How do we ensure that this knowledge is used for good? What are the potential consequences of tampering with the very essence of existence? Section 8. The ethical horizon. As we venture deeper into the quantum realm, we must proceed with caution and foresight. The ethical implications of our discoveries must be carefully considered, and safeguards must be put in place to prevent misuse. The same technology that could unlock unimaginable benefits also has the potential for great harm if it falls into the wrong hands. We must foster a global dialogue on the ethics of quantum computing involving scientists, philosophers, policymakers, and the public. Together, we must establish guidelines and regulations that promote responsible innovation while safeguarding against potential risks. Section 9. Our Quantum Quest. The quest to calculate the universe's wave function is a testament to the boundless curiosity and ingenuity of the human spirit. It is a journey into the unknown, driven by a thirst for knowledge and a desire to understand our place in the cosmos. The path ahead is challenging, but the rewards are immeasurable. As we stand on the precipice of a new era of scientific discovery, we are reminded of the words of the great physicist Richard Feynman. I think I can safely say that nobody understands quantum mechanics. While we may never fully grasp the intricacies of the quantum world, our pursuit of understanding will continue to drive us forward, revealing new wonders and pushing the boundaries of human knowledge.